So yeah, hello everyone. I would like to talk about recent addition of ticking Spinlocks into Zephyr and the initial reasons for all of that. I'm Evgenii Paltsev. I've been working on various pieces of system software for Arc Synopsys architecture and recently for RISC-V architecture as well. All this mostly based on open source projects like Linux kernel, Ubuntu, and some other projects. And after some time, I became the maintainer of Arc processor architecture in Zephyr RTOS. So I spent a significant amount of time making it better for Arc and for others. And thus, I've seen a lot of interesting stuff happening there. And one of them we are going to discuss right now. But first, it's a mandatory cute or funny picture. Here it is. So, a few words about the initial reason why we started to dig into this topic and how it's related to Zephyr at all. Some time ago, I was involved into bringing up of our processors with new ArcV3 architecture, which have up to 12 processor cores. And for this system-level testing, we needed something which is SMP capable, which allows us to load system significantly and stress test it with a lot of inter-core communication and all this stuff. One potential candidate here is a Linux kernel, but it's always challenging to debug issues in Linux, especially if you expect that you might have some hardware issues just because you are just bringing up the prototype. And Linux is too huge, it's too complicated to debug, so for the first steps, we wanted to have something simpler than Linux. And actually, Zephyr is a great candidate for this. It has SMP support, which was added in 1.11 kernel version, and it has matured since then. It has POSIX subsystem, which allows to run existing benchmarks and stress tests without or with minimal changes. And we were planning to support Zephyr anyway. So it's not like we are doing some work which we are going to throw away after that. So it's definitely good. And of course, Zephyr is definitely simpler than Linux kernel, at least for now. At the time, our hardware was not ready. So as usual, initially tests were prepared and run in simulation. In our case, we were using Synopsys and Sim for that. It's our simulator. And such things rarely go smoothly in the beginning. Among the other things, we were bumping into the issue that some of our stress tests were failing. And in the situation when you have a lot of in the situation when you have a new process architecture, you have a lot of things which may go wrong. And the issue can be in lots of places. We may have some flaws in SMP implementation for our architecture easily. It could be some SMP-related issue in POSIX subsystem. We've already bumped into several ones, so it could be yet another one. It could be issue with the stress test itself. It could be issue with some of our tools, like in toolchain or in simulator. So lots of things we can blame here. And after a portion of debugging, we found we bumped into lifelog. And it was possible due to the combination of how our simulation works and how Zephyr Spinlocks are implemented. Obviously, you can just say, oh, it's just the way how our simulation works. Let's just forget about it every time we have something failing on our testing environment. Otherwise, even in best possible scenario, you will end up debugging the stuff on hardware, which would be significantly more challenging. And life logs, it sounds pretty suspicious. Are we the only one who were bumping into such things? And the answer is no. At the same moment, different team from different company was investigated similar issue with Zephyr, but in their case it was hardware platform with RISC-V. We discussed our findings with them, and in the results, we ended in addition of spinlock fairness test and addition of alternate spinlock implementation to Zephyr. But what was the issue root cause after all? To understand that, we firstly need to talk about how spinlocks are implemented in Zephyr. Spinlocks were added to Zephyr with the introduction of SMP support in it. It was done in 1.11 version, and the algorithm itself wasn't really changed since then. Here's the really simplified Zephyr spinlock code. In real code, we are doing lots of other useful stuff. For example, we check for spinlock owner to detect situations when we unlock it from unexpected thread or unexpected core. We might check for the time we spent in this lock when it was held. And we are not simply looping, but we call some special spin relax function so we can still process remote function calls from other cores and potentially doing some power saving stuff. So it's actually a bit more complex, but here is bare minimum. So initially, spinlock was just one atomic variable which was used as a flag. In case of lock function, we turn interrupt off on this core. So the code which is protected by spinlock won't be rescheduled and preempted by some other code. And after that, we try to set this atomic flag if it's not yet set. And in a lock function, we do it in the opposite order. We clear the flag, and after that, we turn on interrupts. It's pretty simple, but there is no fairness guarantee at all. For example, if multiple cores trying to pend for spinlock at the same time, there is no guarantee that one specific core will get this spinlock at any time if there is always someone pending. We can lock and unlock it on on other cores, but never get it on some another core. And now a few words about our simulation. Our simulator can simulate multi-core processor, and in that case, it just run and execute blocks of instructions from each core in single simulation thread. So we execute a block of instruction from core 0, after that from core 1, 2, 3, and after that again from core 0, 1, 2, 3, and so on. And simulation is deterministic, as number of instructions in that code block is fixed, and there is no external events or interrupts, as in this case, there were no peripheral in the model we were using, just because we will bring up in the core stuff. We don't need this peripheral stuff. So what was the issue we were bumping into? We had one spinlock which we accessing from multiple cores. It could be some spinlock in our application, like any spinlock, but in the issue we bumped into, it was just a scheduled spinlock from the Zephyr itself. Spinlock was locked and unlocked multiple times when we execute instruction from one core. But we were always switching to the next core block of instruction when the spinlock was taken. It was just unlucky coincidence, like test was executing stuff in a loop, and the size of this loop interfere with the instruction block size in the simulator itself. So other cores were not able to grab the spinlock at all. It was, and it was scalar spinlock. You can imagine what it affect the system behavior significantly, just because you are trying to get this scalar spinlock and you are not able to grab it at all. And it's not reproduced stably, just because minor code changes may mask this issue. We may like increase or decrease the number of instructions in this loop, so it won't be produced anymore, just because eventually the code would be able to the core would be able to grab this cellular spinlock and test would succeed. So that's why it would be nice to have some test to reproduce it in a stable way. And now we have such test in Zephyr test suite. It's additional test case in a kernel spinlock test. So how this test is done? We just have one spinlock. We grab it, hold it for some time, and release it. And we do it in a loop on all of available cores. We need to hold it for some time just because we need to simulate the situation when multiple cores are pending for this spinlock in a loop. And also we are collecting per core statistics of number of times spinlock was acquired on this exactly core, just to be able to judge if everything is going okay or not. So we have the test. So let's run it on our simulator on NC. We have used, in this example, we have used modified NC-MHS SMP config. We was just bumping number of cores to 4. And where are results? As some cores were more lucky, some cores were less lucky, as expected. But what would happen if we run it on real hardware? For that, let's just take this HDK board, which has 4 ARQV2 cores, and run test on it. Unlike NSIM, unlike our simulator, hardware execute all the stuff in parallel here, just because there's 4 physical cores. So probably we'll get such ideal results when everything is completely fair. Or at least it would be probably close to these ideal results, like this. Well, there's actual results. One core took almost all spinlocks, and all other cores were starved. And it's pretty interesting results, but could we expect it from the beginning? So let's have a look on what was happening. Firstly, let's again take a look on how lock function is implemented. We have atomic read modify write cats primitive. It stands for compare and swap. Sometimes it's also named compare and exchange. So if I use another name, don't be confused with it. It can be implemented. This primitive can be implemented in multiple ways, but it requires some hardware support. For example, some atomic instructions. In this case, we are just using the API provided by Zephyr itself. So we access locked variable in a loop. This locked variable were like internals of a spinlock itself. And we do it from multiple cores simultaneously. And now we need to take a look on our hardware. In our processor, we have a private level 1 data cache. So it's quite common design to it's quite common to have it so on multiple socks. So it's not something unusual. But in the results, the core which own cache line with the locked variable has more chances to this compare exchange primitive to succeed. So if some core get it once, it's more likely to get spinlock next time. How we can avoid such thing? One possible way is just to use another spinlock algorithm with the fairness guarantee. For example, it could be a ticket spinlock. It's not something new. For example, it was added in Linux kernel a lot of time ago, a lot of years ago. So let's take a look how it's implemented. As it was done previously, we turn interrupts off in lock function and turn them on in unlock function. This part haven't changed at all. In case of ticket spinlock, now we have two atomic variables, one for ticket pointer, another for owner pointer. So in the left part, there is a diagram. So we'll show how multiple cores would be try to take this spinlock and what interval states we will have. This core just marked this, started with number 2 instead of 0, just to not to be confused with owner number. This owner doesn't relate to CPU ID at all. It's just completely different numbers. So core 2 try to get spinlock. It increment this ticket variable, and it stores local copy of old value of this variable internally. And after that, we try to check the condition. If the owner is same as ticket, if the owner is same as all value of ticket, we can get this spinlock. And in this case, previously, ticket was 0, owner was 0, so core 2 get the spinlock and hold it for some time. After some time, core 3 also want to grab the spinlock. It's same go to spinlock function, increment this global ticket, so it now would be 2, and hold the previous ticket value locally, and this previous value would be 1. And now it waits for the condition what owner would be equal to the old ticket value. But we haven't modified owner just because it would be modified in a unlock function which we haven't called from the CPU2. Now another core try to lock this same spinlock. It would have ticket value 2, and it would be waiting till owner would be equal to 2. So now we have something interesting. Core 2 decided to release this spinlock. It's going to this unlock function and increment this owner value. And now there is potential to threads which can grab this spinlock. In previous spinlock implementation, there was no guarantee if it would be core 3 or core 4, because they are both spinning in one variable, and who was lucky when he gets spinlock. In this case, it has deterministic behavior. So because core 3 is waiting for owner value to be 1, and core 4 is waiting for owner value to be 2. Now we have owner value to be owner value 1, so only core 3 can now take spinlock. So it's take it. After that, it's release it, and we increment this owner to 2, and now core 4 can finally lock its spinlock. After some time, we have this spinlock unlocked. So again, both owner and ticket would be in the same, would have same value, and it's would be incremented after that when someone would try to lock it again, and after some time this value would be wrap around, but there is no issue just because it's totally fine by this algorithm. So now we have ticket spinlock implementation, and let's run our test with ticket spinlock implementation. Firstly, on NSYM. And as we can see, it works nicely. Everything is completely fair. So let's try it on hardware platform on this HDK board. It's also completely fair. According to our tests, it's just nice. So let's run it on something else. For example, on QEMU. We have used modified QEMU Cortex A53 SMP config. We just bump number of cores to 4 to be same number as with other tests. So for now, everything is OK. It's fair. But what would happen if our host is a bit busy? For example, you may feel urge to backup def random into def null, and you want to do it in multiple threads. So here's a simple bash script to do that, which allows us to nicely load the system. So all the cores except 2 would be running this copying of def random into def null. And here's a screenshot from top, so everything is pretty loud. So let's run it. Let's rerun test on QEMU. And now we have some issues. Results are not perfect anymore. But what happens here? We have some flow in Spinlock implementation itself. Let's check. We launch QEMU with SMP option. It's SMP CPUs and number of CPUs. So it spawned multiple threads. It will be a thread for each core. So in case of we have 4 cores in Zephyr, we will have 4 threads in a host, which would be representing each core. So in ideal situation, we will have a Zephyr test thread running on some host core. But if we have high load on a host, QEMU threads would be more likely to schedule it out, and it would be happen on different amount of different time moments. So as it was shown here. So if Zephyr thread requests Spinlock, it still get it in proper order. The algorithm itself is okay, but the issue is in another place. Zephyr thread, which would be requesting this Spinlock, may not request it as QEMU thread was not running at all, just because of it was scheduled out on a host. So this thing is obviously cannot be fixed with ticket Spinlock. Yeah. So we improved the situation with Spinlock fairness, at least on some platforms. Do you have any drawbacks with ticket Spinlock? First thing which comes to mind is slowdown. Spinlock is the part of a code which is used often enough. We have more logic in Spinlock function, so have we made some noticeable impact on the system performance? But let's first compare how our old and ticket Spinlock implementation was done. So in case of new implementation in Spinlock function, we have +1 atomic get Zephyr primitive, which would be result in 1 memory read and 2 memory barriers. In case of Zephyr, it would be full memory barriers. And in case of KSP unlock, it would be atomic read modify write instead of regular write. Number of barriers would be same just because we are replacing one atomic primitive with another. So it doesn't seem to be really big change. And in terms of how we access the global variable, there's also no real difference. In both implementation, we just spin against the global atomic variable, and we are trying to do read modified write access from the loop, from the Spinlock loop. But in real system, it may have some impact depending on the architecture, because with atomic implementation and barrier stuff would be significantly different impact on different architectures. So in case of Arc, we don't have something serious. But there is another thing in this alternative Spinlock implementation which may concern us. There are 2 independent atomic variables now, and is there a chance that they may unsynchronize on some point? Everything would be fine if we just have a lock and unlock function. But we also have a k-spin try-lock function, which try to lock Spinlock if it is available and do not spin if it is not available. And it has tiny window where we have we may have potential issues. The window is between atomic get and atomic compare and swap primitive. It was marked with this arrow. It's just several assembler instructions where we need to atomic variable to wrap around to have some issues. So what we may do wrong while executing these several assembler instructions. For example, we may try to call a lock function with a huge amount of times, with almost uint 32 max value plus something. But as we have lock function blocking, it would require us to have this huge amount of number of cores in the system. So obviously it's not the case, especially in case of Zephyr. Another thing we may lock another option is to grab and release spinlock with, again, huge amount of time from other cores. And after that, to lock it again. If we can do that, we can close the wraparound. But it needs to be done while we executing just several assembler instructions in the context with locked interrupts. So we cannot jump to interrupt, we cannot reschedule. So it's not really possible for our Arc Zephyr port. To meet such conditions, we need CPU core just to hang, which would be much problematic issue if we just have CPU cores hanging. So we've talked about why it won't happen, but let's talk about why it may happen. Potentially, we may run Zephyr on top of some other software. For example, in case of RISC-V, it could be machine mode software if we implemented RISC-V Zephyr port, which would be running in the supervisor mode and not in machine mode like it's done right now. Or we may run Zephyr in virtualization on top of some hypervisor. So now we can imagine some specific use cases which don't require our hardware to be broken to bump into this issue we were talking about previously, about wraparound. So how we can fix that? We may actually there's multiple possibilities. We can use double atomic instructions to access both variables simultaneously, so it will be just one atomic access. But we don't have such API in Zephyr, and most likely not all the architectures which support SAP in Zephyr has such instructions in hardware. Another option would be to store ticket and owner in halves of one atomic variable. So it would be 16-bit for one for the ticket, and 60-bit for the owner. It would be easier, however, we won't be able to use existing atomic increment primitives. We need to implement something on which is based on this compare and swap primitive. So it's definitely possible, but for now it's not yet implemented in Zephyr. So we've discussed ticket spinlocks, their advantages and drawbacks. They are available in recent releases. However, they are marked as experimental feature, so it's not enabled by default. So you can use them wisely, and if you have any questions about it, we have some time to ask.
Wait. Okay.
Yeah, so obviously the intended experimental feature is that it will mature over time. I don't know if it's turned on or maybe I got too far from the transmitter. The intent of the experimental feature obviously is going to mature over time, and that eventually will turn it off. It's been a while. It sounds like you've got it running on hardware reliably, like you're running the full Zephyr test suite, and in that on that? Yeah. Mm-hmm. Right. Right. Yeah. So I guess my input would just be, I mean, I think it's time if you guys are willing to say, hey, you know, we've got this suite and it's been running on this platform in our rig or whatever. You know, the intent was always that it be turned off and that we start using this more broadly, and then we would move it to like this or that, you know, emulation platform would be running it all the time. And
well, actually, we already have it enabled for our platforms, for our platforms, and we have it enabled for one of the QEMU RISC-V platform. So it would be tested in the Zephyr upstream CI. And generally, it would be a good idea to have it enabled for other platforms, but again, we need to be careful just because there are some potential issues with implementation if we are running in some virtualization.
Right. Yeah. Exactly. We wouldn't move away from a default spinlock for a while, but I mean, again, the next step after experimental is, you know, an available option.
Yeah. Probably as we are currently doing a lot of stuff with RISC-V as well. At some time, we are going to implement this S-mode port of RISC-V in Zephyr, and for that, it would be probably one point in checklist to have this spinlock implementation updated so we won't have this potential issue at all. Just because there are already implementation in some other projects after we found it, so we can use it as well.
Sounds good. And the other question was going to be, are you aware of any progress actually localizing the original live lock that was reported? I'm just interested personally. Obviously, I was a big thorn in this, you know, saying that like, look, I mean, you know, the scheduler lock just doesn't have that. The, you know, critical sections are all small. I can't see any circumstance where you would then, you know, get stuck in a dueling lock where one party was unable to progress. I don't know if there's
yeah, actually, I've mentioned about it, and yeah, let's just open the proper slide. So yeah, the initial live lock issue was due to how our it's not the thing I was showing.
Oh, it was purely the simulator thing. Yeah. Okay. So
yeah. Okay.
The number of blocks that then determinizes the order in which the locks are taken. Okay. All right.
Yeah, it's a pure simulation. It's just because we are not doing it in parallel. We are doing just it by bunching instruction, and as it was deterministic, if we get this situation, what we are always graph the lock, and after that simulation would be taking a bunch of instructions from another core. The other core would be seen as this spinlock is always taken.
Okay.
So it's it was mostly due to how our simulator works.
That's all I have. Anybody else?
That's actually a question on YouTube, so I'm gonna read it. It's from Wilfried. And Wilfried is asking, some platforms don't support cross-core atomic operations like the RP2040. Would Ticket Spinlock be portable to such platform requiring SoC-specific primitives, for example, using hardware Spinlock?
That's a good question, and probably to answer that, I need to check how the hardware Spinlock are implemented, but generally, even the original Spinlock implementation required to have these atomic read, modify, write variables. So I'm not sure if and how this original Spinlock was implemented for them, but if they use some other things instead of this read, modify, write atomic instruction, probably it could be a way somehow to implement it, but I need to check this hardware specific firstly.
Yeah,
it's really have a lot of influence on how we can or cannot implement it.
Right, we had a driver submitted a while back that was a hardware spinlock, and in that case, the hardware actually managed the fairness management. That you didn't need a ticket spinlock because the operations at the hardware level were like lock and unlock, and it would handle that all for you.
Yeah, that's true, but
different hardware, yeah.
Yeah, that's true, but there's no information if the hardware maintain this fairness or not, and if it's not, then probably they want somehow to work around it.
So I think there is actually another question to that person. So I don't really understand if true SMP system could be implemented with such a memory approach, because if there is no coherency between cores, so how that could be even possible? And that question then makes no sense, because all of what we had in that presentation, it is related to SMP system only. Because in AMP system, there will be another way of synchronization things, and on single core system, there is no problem at all. So it is kind of a question without or taken out of the context. So yeah, I don't know. Typically, those kind of things which we are seeing here, they are implemented on top of the cache coherency protocols. And so if you don't have cache coherency, there is no such kind of primitive at all.
There can be, like extensive, for example, is a cache incoherent architecture. It actually does have an atomic primitive, it just goes through the cache. So different hardware is different.
Yeah, possibly.
Yeah, I've seen these hacks for Extensa, but I never actually investigated how it's done for them, just because luckily we don't have such a requirement.
All right, we still have time for a few more questions, if there are any. Not on YouTube, not in the room. All right, thank you.